This one?
No. Yep. This one doesn't go. Well, I need this mic or just project.
Yes, please.
Okay, welcome everybody. Apologies for the delays, but fortunately we have the entire hour today. I was hoping to grant 30 minutes to everybody more of work, but it will be just 20 minutes more because 10 minutes was spent with these difficulties. Anyway, so I'm very pleased to introduce today Michael Terres. So he's recently joined the CfA as a postdoc at last September, right?
Yep.
Yeah. So Michael earned his PhD at the University of Alabama, Huntsville in just last year, 2023. He worked with Dr. Gang Lee to investigate turbulence role in energy dissipation in the solar wind. And is currently working with Mike Stevens as part of the Parker Solar Probe suite team, which is the suite measuring the plasma properties in the solar wind. And his research interests also include MHD turbulence, kinetic physics, and particle acceleration in the solar wind, and also in Earth's magnetosphere. I'm very pleased, and we had a very interesting conversation also on energetic particles. So the floor is yours.
All right. Thank you to the organizers for helping me get this set up. And sorry again for some technical difficulties on my end. Who knew a microphone was not being on my laptop was going to be this big of an issue. But regardless, I'm Michael Terres, as Federico announced. I just defended, so I'm just new to the postdoc life. So I'm going to be presenting today on some of the work I did for my dissertation and some of the extensions I plan on working on here at CfA in the coming months. There we go. So just to go ahead and give a brief introduction of what's going on, and what I actually study is we take a look at our local star. And we have all these interesting, unique areas where very different physical phenomena are going on. And I only care about the corona and the upper part of it. Now, when I say that, this whole system influences what we see in the solar wind, what we see in the upper corona, the various wave generation mechanisms are all generated from convection zone physics to the chromosphere variations. So it's a very interconnected system that I eventually want to be able to connect and provide a full picture of what's going on to help explain some of the signatures and heating that we end up seeing within the solar wind and the corona. So just to kind of give a basic overview and review of how the solar wind was kind of discovered, I just really like having SOHO images because we can kind of see exactly what this solar wind and what we're talking about is. What we can generally see is this is a comet coming in toward the sun, and if we look at the radial, the tail of the comet, we always see that it points radially away from the sun, giving us a hint that there's constantly an expulsion of plasma from the upper atmosphere of the sun, which is the solar wind. And it was initially predicted and supported with a dynamic model by Parker in 1958. So when it comes to the solar wind, we need to do a couple classifications that are really important, especially when it comes down to the different types of turbulence that are occurring in these regimes. And I'll touch on that in a little bit. But typically what we'll find is we have fast wind streams, which happen near the polar, the holes in the north or near the north and south poles. These are the high fast speed streams. There generally everything is flowing out. And they're dominated typically by just alphenic fluctuations or just outward fluctuations of some sort. Near the equatorial region, we start to see the formation of the slow wind. And that slow wind period is a lot more interesting and evolved because we can have the slower speed means we have longer time to look at the evolution of turbulence. Different physical processes are happening in each region. The temperature and density are different in either of these regions, so they have vast implications on what's happening within the solar wind. And just to point out here, what we can actually see is there's a solar cycle dependence. So at solar minima, we get this nice structured solar wind distribution, whereas at solar maxima, we get a mixture of fast and slow streams and really leads into the dynamic nature of the solar wind and corona. So the reason we know that turbulence is kind of playing a role is coming back down to the signatures of active heating. So if we just take a radial plot of the temperature with respect to distance, this is in astronomical units going from from the sun out. If it was just expanding with no active heating, we'd expect an adiabatic fall off, which is represented here in green. And what we actually see from Voyager observations going out really far into the interstellar medium now, we see that the temperature is well above what we'd expect from an adiabat. And then if we actually look at near the sun observations, so these are from Helios, we can look at the parallel and perpendicular temperatures, which just tells us the relative heating along the magnetic field or perpendicular to the background magnetic field. You start to see that there's anisotropies that develop, which further lead to this turbulent nature, developing some instabilities that will grow and provide dissipation and heating mechanisms further in the process. So just a quick review of what turbulence is and to connect kind of the different areas of where you can look at turbulence and how it's all interconnected. We typically see turbulence in the hydrodynamic sense here in oceans, rivers, stirring a cup of coffee. It's a very efficient mechanism for dissipating, transferring energy, and mixing all these systems. Now in astrophysics, we see just these examples in stellar atmosphere like the solar wind and the corona. Accretion disks, galaxy clusters. I'm sure there's many more that examples exist, but these are just a few that I kind of wanted to broaden the scope of what this work can connect to. So when it comes to observations within the solar wind, what we're typically looking for is what you do with any kind of turbulence study is you look at the statistical properties. And one of the most important and powerful tools we have in turbulence is looking at the power spectral density. So the power spectral density, and I show an example here on the right of this slide here. And what we can kind of see is you have a frequency correlation at this large scale, which tells you that there's some random large scale motions in the system. And then in a hydrodynamic sense, you would have a velocity fluctuations of the fluid turning that would develop non-linearly, creating a nonlinear cascade, which is represented through this inertial range that'll continue at a constant rate all the way to the point where you reach dissipation, where you can have viscous effects in the hydrodynamic sense. And MHD, you need to take into account the particle resonance conditions. And I'll touch on that in a slide or two. So when we talk about these power law scalings and what we're looking for in observations is typically, do we see a 5/3 or do we see a 3/2? So the 5/3 is referred to as the Kolmogorov spectrum, and this comes from hydrodynamic turbulence. In the solar wind, when we see a 5/3 spectrum, it is not from hydrodynamics. We have the presence of the background magnetic field, and observations still are able to give us this -5/3 observation. So one of the leading theories of how the turbulent cascade is developed is actually you'll have counterpropagating Alfvén wave packets. So these are just fluctuations transverse to the field that move along the background magnetic field direction. They can interact through nonlinear shears, gradients, and as a result, you can generate the nonlinear interactions that you need to drive the turbulent cascade. And if you just take that simplistic picture of just counterpropagating waves and everything's isotropic, you can end up recovering this, the Oroshenikov-Krakinin spectrum, which is just the isotropic MHD extension of hydrodynamic turbulence into the solar wind. Now, what we actually see in the solar wind and what has widely been kind of accepted, but not accepted, it's still highly debated, but one of the most commonly referred to turbulence theories is this critical balance phenomenology. And essentially all critical balance goes on to say, proposed by Goldrush and Sridhar in 1995, is you have a balance of the Alfvén time scale, or the time it takes an Alfvén wave to propagate and distort the system. And then you have that's balanced with a nonlinear time, and that's the nonlinear interactions, in this case, between counterpropagating Alfvén waves. As soon as you do this, the nonlinear interactions are going to be occurring perpendicular to the background field, whereas the Alfvén fluctuations are traveling along the background field. That automatically sets up the system to be anisotropic. So what we find in the solar wind is you'll have a different power spectrum perpendicular to the background magnetic field than you would parallel. And this is generally the most probably well-developed and subsequent revisions to this theory have been made on the critical balance alignment. And much of my work starts from critical balance, and I'm looking at some of the extensions that I'll touch on here, mainly about dynamic alignment, and I'll touch on that in a few slides. But ultimately, regardless of the turbulence model you take, what we see in the solar wind is we do see this clear bend over break scale at the near ion scales. And this is a signature of where we're having energy dissipated from these large scale fluctuations down to the kinetic physics and the ion populations, electron populations themselves. For instance, at this scale, this is the ion scale, this is where we actually start to see our first signatures of heating from the MHD waves interacting with the ion population themselves. So at ion scales, we typically need to just consider the kinetic physics. So whenever we talk about kinetic physics, we're looking at the distribution of particles. So here are some examples of the ion velocity distribution function. We can see field-aligned beam structures. We can see temperature anisotropies, in which we have heating perpendicular to the background field, heating parallel to the field. And all of these give rise to various fundamental physics that can be happening within the solar wind. So whenever we see some signatures of parallel heating, you can have physical mechanisms like Landau resonance. You can have cyclotron resonance, where you generate a cyclotron wave and it would lead to the perpendicular heating. Inversely, if you have perpendicular heating, you can drive other instabilities that in turn provide ways to dissipate turbulent energy. So this is, overall, this is still an open question that everyone's still trying to figure out, is what various plasma systems provide different means of dissipation, or do we see one more relevantly in the slow wind versus the fast wind? So that was kind of the motivation for my first study that I did early in my PhD. And this was to take a look at what the dissipation scales are within the solar wind. So just to give a quick overview, I'm going to go through this a little bit quicker than I'm going to do my second half of this talk, just because this kind of primes the second half. But there are three possible scales that are typically associated with dissipation of turbulent energy within the solar wind. Those are the ion gyro radius, which is just simply the radius at which the particle rotates around the background magnetic field, strongly dependent to the strength, strongly connected to the strength of the background field. The ion inertial length scale, this is typically associated with the thickness of what current sheets are. So you can start talking about magnetic reconnection. And also the Hall MHD, so the electric field terms, start to become very important. And then you have cyclotron resonance, which I mentioned before. You just have these cyclotron waves generated at a particular frequency that resonate with the background population, transferring energy that way. More recently, there's been this proposition of this disruption scale. So the idea is you take the critical balance phenomenology, and instead of it having the same nonlinear interaction or the nonlinear time scale as a function of all scales, the nonlinear time scale itself is actually scale dependent. All that goes on to do is, instead of having this rope-like structure that you'd see with a critical balance eddy, you end up seeing this thin ribbon current-like structure that's generated within the system. It becomes susceptible to the tearing mode instability, magnetic reconnection occurs, and you can have the injection of energy through that process. So what we ended up doing is we wanted to take a look at observations that aren't really, are not typically used to do these sort of studies. So we took a look at the MESSENGER spacecraft. So MESSENGER gives us a nice opportunity to investigate this radial evolution, because we have 3 planetary flybys of Mercury, 2 planetary flybys of Venus. So if we actually look at the solar wind plasmas on either side of these planetary crossings, we can get an idea of maybe a radial trend of how the plasma is evolving. So we can look at the power spectral density, identify the break location, and see how it evolves. And that's exactly what we did. One limitation we do find is that we don't have any plasma data for this event. So this is just an example of what the magnetic field data looks like. I go ahead and take the power spectral density on either side of these regions here. I can go ahead and get the fit that using a functional form based off of a broken power law and get an estimate of what the break location is going to be. But interestingly enough, in these periods, is we see the generation upstream of each of these planetary bow shocks, we see the generation of 1 Hertz Whistler waves. So 1 Hertz Whistler waves show up in the spectrum. I just show it here as just this little bump frequency that is particularly defined based off the strength of the background magnetic field. So we know that just simply from the dispersion relation of what a Whistler wave is going to do. The exact generation mechanism isn't well understood of how Whistlers are evolved, but their physics and their studies are well documented throughout the many years of study. So what we ended up doing is we're just like, well, what happens if we take a ratio of the break scale in this bump location and plot it as a function of radial distance? Do we see any trends? And what we end up finding is if we go ahead and do this, the ratio of the break and the bump location, we can go ahead and see that their values with respect to radial distance are constrained to relatively narrow bands. And we can almost argue that they stay constant throughout all these periods. So we make a general claim that, okay, based off of that, if we know that the bump location itself is based off the magnetic field strength, we can then infer possibly that the break location depends directly on the magnetic field strength. So we take all our observations and we go ahead and we do a linear fit with respect to magnetic field using this functional form, and we can solve for this delta parameter, which just tells us how the break location scales with respect to magnetic field. I use cyclotron resonance scale or frequency here, but that's just magnetic field with a few extra terms on it. Then we take those 4 characteristic scales and we do a simple dimensional analysis to go ahead and see how the magnetic field scales with respect to each of these dissipation lengths. And what we end up finding is that the cyclotron resonance scale and that our disruption scale, which is defined by that dynamic alignment phenomenology of the turbulence, are in pretty good agreement with our results. So we end up making the final claims in this work that obviously there's probably not one prevalent dissipation mechanism. There's a mixture of both depending on the plasma environments you're in. We already know that the plasma beta, which is just the ratio of the thermal to magnetic pressures, are going to be a good indicator of what scales might possibly occur. But this led to the question of, does dynamic alignment actually occur within the solar wind? And what we can go ahead and see and investigate is, or what we want to investigate is, do we actually see signatures of this? So just returning back quickly to the critical balance phenomenology, again, all we were saying is that the nonlinear time scale is equivalent to the Alpine time scale. And what dynamic alignment does, and I hinted at this a little bit before, is dynamic alignment ends up assuming that you have a reduction in the nonlinear interaction time as a function of scale. And it's simply just modified by this sine theta, where this theta is the angle either between velocity and magnetic fluctuations, or in this case, it could be Alsacer fluctuations, where Alsacer fluctuations are just simply a combination of velocity and magnetic fluctuations, and you just change the plus or minus sign to determine z plus or z minus. So once you introduce this dynamic alignment and this reduction of the nonlinear interactions as a function of scale, what you can end up getting is you no longer have this tube-like structure. We start to see this flattening occur. So how do we end up measuring this within the solar wind? Well, we can actually take the variations in increments. So I show here with respect to the Alsacer variable, which is just z plus z minus represented in the diagram here. We can also do this directly with respect to the velocity and magnetic field. And when we say increments, we're just talking about two time points, their difference with respect to time. And we can vary this to get a scale-dependent model of how this alignment angle would evolve. So previous observations looking into the dynamic alignment angle, I'll use the structure function, and it's a technique that I use in my study. We show that generally from the outer scale going down through the inertial range, as mentioned earlier, we see this general alignment. However, once we start to reach small scales, we see a deviation from this and this anti-alignment process. And this was typically attributed to the noise fluctuations within the data. But we weren't quite satisfied with that argument because we know as we get close to the dissipation scale, you can have features such as like intermittency or other structures, different turbulent modes can start to enter the system, and they possibly may be describing or could be used to describe why this anti-alignment occurs. So what we end up proposing is the dynamic alignment phenomenology is based off the idea of counterpropagating Alfvén waves in which you have equal amounts of inward and outward flux of fluctuations. However, in the solar wind, it's always dominated by outward Alfvén waves. So we have a subdominant population of inward Alfvén waves. But what we end up saying is we'll have dynamic alignment, and we make the hypothesis that dynamic alignment only occurs between these Alfvénic fluctuations, as prescribed by the previous theory. And then we can have a subpopulation of turbulent fluctuations, which we refer to simply as structures. And for sake of brevity, I won't go into what those structures are now. We have a couple ideas, and I'll touch on those at the end. But we break it into a two-component model where we have only purely Alfvénic fluctuations, and then we have this structure component. Upon making this contribution, we can go ahead and look at the correlations with respect to the newly defined decomposition. So if we take the correlations of these fluctuations, we can break it into only the wave contribution and the structure contributions. I keep velocity and magnetic structures, but they can actually be separated later on. I go ahead and make a general assumption that the inward flux is some scaled ratio. The magnitude of the inward flux is some general relationship between what the outward flux is. And then we can go ahead and reconstruct what the cross-helicity and residual energy are, which cross-helicity, residual energy just tell us the measured balance of inward and outward waves. That's for cross-helicity. So that tells us the imbalance of the flux. Whereas residual energy just tells us are we magnetically or kinetically dominated, which fluctuations are occurring more. So using these relationships, we can go ahead and we go from the residual energy and we actually back solve for what this zeta parameter is, just using some simple algebra. And we can get this general expression. And then we invoke the claim that we have dynamic alignment. And we require that it exists. So I'll come back to all of that just for, I want to get through this a little bit. So what I do is I take this model and the general theory that we have, and I go ahead and apply this to Helios observations. So I look at the Helios 2 spacecraft from 1976 to 79. I select periods that are within the slow wind. The reason I choose slow wind is typically within the slow wind, the cross-helicity is closer to zero, telling us we have more so of a balanced flux of inward to outward waves. Now, also within the slow wind, it's more dynamically evolving, so you have more structures that are convected out with the wind. So there's some limitations with choosing slow wind. We then go ahead and require that we have 3.5-hour data intervals for our averaging. So I think our longest period is 9 hours, but our smallest period has at minimum 3.5 hours. And we require that the in-situ data has only 1% data gaps. This made my life much easier because we ended up with 90 periods, and then we could go ahead and reduce that further to some 20 events. So what I end up doing and what I'm actually calculating is the second order structure function. So what we're looking at here is just an example of the structure function. What we see in the top panel is we see the energy contained within the outward Alsacer fluctuations. In black is the magnetic fluctuations, green is the inward Alsacer fluctuation, and V is velocity fluctuations. And what we can tell from this plot already is kind of an example of what I showed here on the bottom plot, is we see that there's more outward versus inward flux, just in total amount of energy. So that's this blue curve here, which is the cross-helicity, which is some value near 0.5. And then we also see that this period is magnetically dominated versus the kinetic fluctuations in red. So we also see that again in the residual energy. So I calculate this for all 20 events that we go ahead and find. And then I define the dynamic alignment angle, which I use the formula I showed earlier. I should actually include that here. And what we're looking to see is, does this dynamic alignment angle actually have a scale dependence to it? Some of the traditional theories that have been out there propose that the dynamic alignment angle should scale anywhere from 0.2 to 0.1. But what we're really trying to see is, do we actually see this trend that from either the outer scale down to small scales, you see this gradual alignment? And for our first event, which had relatively balanced amounts of inward and outward flux, we do generally see that there is some clear alignment. But again, we reach a scale about 2 × 10⁻³ hertz, where we start to see the anti-alignment in both. Again, this is another example where we have only outward flux. Looking at the inward flux, it's basically noise. And then we see very high correlation between velocity and magnetic fluctuations. So this period itself is an example of highly alphenic flow within the slow wind. And if we look at the dynamic alignment for this event, we see no clear dynamic alignment, which is expected to our initial hypothesis that we only have dynamic alignment when we have inward and outward propagating alphene waves. So I developed this very lengthy, very simplistic model, but also when you look at it on a slide like this, looks very daunting and kind of gross. But we go ahead and we just enforce the dynamic alignment requirement, and we leave a free parameter alpha, and we go ahead and we're going to test various alphas to see what would give us the best fit. And then we have 4 model parameters based off the theory: this zeta, the relationship between inward and outward flux, total structures in velocity and magnetic field, and then we require this alignment angle to hold. And then we have 3 observations, so we go ahead and we can solve our system to go ahead and find a case where we reach the minimum variation, which is just a parameter we define ourselves. So applying this model to both of our events with various different alpha parameters, looking at different alignment scaling, what we can see is that the ratio of inward to outward flux for our first event confirms with what we see from lacrosse helicity. But our biggest finding is the growth of structures at these small scales. So this evolution of these structures is kind of saying that you have not just the typical alphenic turbulence, but you have some subpopulation that's possibly creeping into your system, whether that's a velocity fluctuation like through shears or quasi 2D turbulent mode. That's to be discussed further. So, but if we look again at the second event, which had no inward flux, represented kind of here with this really small ratio of the black curve, when compared to this, we see that it's about 0.3, about half the power. In this event, we see no inward alphenic contribution, but we do see this rapid growth in structures. So we go ahead and we take these general results and we plot this for all 20 periods. And what we do see is that there is always a subpopulation of the inward flux, and we see a decent amount, well, a varying amount of inward fluctuations to outward fluctuations. We then also see for every event that we see a general increase in what these structures are. And we attribute these to either likely compressive or velocity structures. And this is kind of leading to the work that I want to go ahead and do here, and I'll go ahead and start wrapping up. Just to kind of leave it here and touch on the last couple points, what we ended up doing, we just kind of looked at the dissipation scale, found that there's possible signatures of dynamic alignment through this tearing mode instability, being in agreement with what we see in observations. And then we've further tested and are working on looking into the dynamic alignment observations. And we have some speculation that you start to see the growth of kinetic or velocity fluctuations as a function of scale. So I will go ahead and leave it off here and open up to questions. And if anyone would like to chat, I'm more than happy to chat about this. So
Thank you so much. Any questions?
So thanks so much. But one thing I'm kind of curious about is how the dissipation itself relates to things like these ingoing and outgoing waves and their ratios. Because I mean, what's setting the local thermal temperature versus or the beta essentially locally in a patch is how much local dissipation there is, right? So doesn't this all kind of like
and that's exactly so that's exactly what we need to do, and that's part of going to be my continuing work, is do more of a statistical study of saying, this plasma regime has a plasma beta of these parameters. We know what the density fluctuations are. We know how everything's kind of evolving. And then we can characterize and say, oh, this is the likely, given these solar wind parameters, this is probably the possible mechanism. Because I can already tell you that the disruption scale can only happen when your plasma beta is within a particular regime. You have to be magnetically dominated in order for it to occur.
Right.
So it's not generally going to apply to all of the solar wind. So I mean, it would be foolish for me to come up here and say this is the process happening everywhere, because I know for a fact it's not. But characterizing where it's occurring, that's the next step of that study. So yeah, that's a great point. Yeah.
Questions? So the all these structures, what's your insight? Are those related in situ, or they're more likely to be carried out
So
atmospheres of some?
yeah, so we don't have a clear answer right now. We speculate, and we would like to think it's related to some intermittent effect, so it would be generated in situ. However, talking with some colleagues, it could also just be advected structures that are existing and evolving in the system, some small turbulent subpopulation, say. And once you get to small scales, they're just existing and they're just advected out with the wind. So we don't have a clear distinction of whether they're just generated locally or already from the solar surface and just propagating out. That's going to require some future investigation.
Other questions? Do we see any question online? No.
Just should I just get out of the slides?
Okay, let me. We don't see any question online, but please, if you have a question, speak up. Yeah, please.
This may be a rather off-the-wall question, but is there ever any evidence for reconnection going out appreciably from the surface? With these inward and outward flows, I would think that this might arise, does it?
Yeah, so there are observations of reconnection. From what I remember, it's been a little while since I've gone through it, but typically you can look at the reconnection kind of exhaust where you have the population, you have the ion population will end up trying to follow the beam, so you can see a bifurcated distribution of particles. So yeah, there are definitely in situ signatures of magnetic reconnection, a lot within the magnetosheath, but even within the solar wind, there have been observations.
Thank you. Other questions?
Can you say something about critical balance in the slow versus the fast wind? You mentioned that in the slow wind, the cross helicity is close to zero.
Yeah.
Does that imply that critical balance is less likely to occur there?
So the original formulation of the critical balance argument requires a balance of inward and outward flux. You need to have very similar amounts. What we see in the solar wind is they're very highly imbalanced. Everything's generally flowing away. So within the slow wind, you're typically able to get to regions that may have more of this inward flux. So you might, as I mentioned with the cross helicity, it becomes closer to zero, but it's never actually balanced. We always see that there's a preferential direction. So there's been extensions of the critical balance phenomenology to the imbalanced case. And that's a very active area of research. But in the fast wind, depending on who you discuss with, some will argue that critical balance can't exist within the fast wind, just because you have only outward flows versus inward. Whereas the slow wind, it's a little bit more up for debate. So that's kind of the reason we went slow wind, just because more likely to hold there. But yeah, that's still actively being looked into. Yeah.
Any more questions? If not, let's thank Michael again.
Yeah, had a lot of stuff to go through, and I was just like, oh no.
Almost everybody stays until then.
Hey, thanks.
Thank you. For your- I saw him and I was not because my continuous now. Wi-Fi issues. I was just